So we are going to start with operators, operator values, and identities, and continue our how we try to see how we try to see showing the equation via different approach and conflicting or maybe approach not conflicting approach or complementing approach of reaching the same result. Even though the interpretations may be conflicting. So, in today's class, we are going to have the thing is that we are going to have how we study operators, operators, eigenfunctions, and eigenvalues of physical entities. Physical entities. So we are going beyond mathematical symbolism, and we are trying to give meaning to those symbols vis-a-vis some measurable physical quantities. The physics, the math of mathematics to physics. So in that sense, even though maybe two operators in quantum mechanics can generally be, there can be two elementary operators, which can be differential operators. For example, d by dq with the multiplication by q. So before coming to this operator, what I should say, specifications, where, for example, operators was a technical way, for example, how we can arrive at from this side to how we can arrive at chi q by some matrix transformations. But sometimes those matrix transformations had the similarities, which was as operator, and we just somehow merged the definitions of operator and matrices. So it was a way of going from one function to another function by some transformation. But here, the same definition of operators, now we are going to have construction of elementary operators. For example, this differential is multiplied by this. Because the coordinate function for a given function, the functions can be d psi by dq and coordinate psi. So the construction of more complicated operators can be given. That's it. So for a given mechanical problem, if we have canonical parameters, the way we have canonically conjugate variables which are associated. For example, in classical scheme, the canonical parameters with P1, P2, so on, and Pn, and a physical entity U is, which is determined classically. It's the function of parameters. U is function of parameters. Un. P1, Pn. And we may assume that U is a polynomial in Pi, U is polynomial in Pi, and Q is the operator. Q is the operator by Qi multiplied by Qi. So now you can say, for example, FQi, the operator, and the multiplication is that of FQi. And if Pi to Pi, the operator can be like this, d by dqi. And in the same way, if it's Pi square, can have a square of, the operator can be h by 2 pi iota d2 by d2i square, so on and so forth. So U operator, so the Hamilton H can be written as, for example, energy H, total energy H can be written as, it's like H square by 2m del square. So if you want to write it in terms of operator formalism, so it's H 1 by 2m is outside, H by 2 pi I iota square. It's d2, this qi, you can take x, y, z, means 3 coordinates, we have 3 coordinates, or q1 square, q2 square, or q3 square, so on and so forth. And this is the potential q1, q2, q3. So now, so this is a general, in the simplest cases, how we can write energy in terms of operators. But now in this technical sense is that how we can go from operators to operator eigenfunctions to, we can have eigenstates, and those are operated by operators, and then we have eigenfunctions, and how we can at the end arrive at eigenvalues. So that's it. So eigenfunctions and eigenvalues. So the question is, if there are maybe two or more eigenfunctions, whether if we change the order of the operators in a given chain, will it say anything fundamentally something different? So it turns out in quantum physics, not in classical physics, the two commuting operators two operators may or may not commute for a given eigenfunction. So that's the basically defining thing, how we can differentiate between classical operators and quantum operators. So it's a commuting property, which is an important property which we are going to focus. But before we are coming to commuting property, how do we just make some sort of reasoning, how to justify it in that way, and that two commuting operators may not commute. What's the condition? How do we arrive at it? So, for example, the first Schrodinger equation, which is called time independent Schrodinger, can have the following form, which means that u operating on this function gives u of pi of q. So ui constitutes the set of eigenvalues of entity u, and which can be a discrete set of eigenvalues, So an operator operating on a given state will give an eigenvalue which may be a discrete set of eigenvalues. Now the thing is that and phi I k are the solutions of these equations. So phi iq constitute the eigenfunctions. They constitute the eigenfunctions. So in the same way, u operator acting on this is ui phi of iq. So you can have not a single value. You can use the words of this analysis. You can have manifolds of values, a class of values which may be satisfying them, and those class of values may be part of some manifold. So a sort of geometrical intuition, a particular way of how we do those class of eigenvalues of spectrum of discrete spectrum of values. They can be found have their representation in a manifold, and that manifold is a continuous manifold. Such that they since normally these states, so if they are of the same class, they may be orthogonal in that consideration, and they may be continuous set of orthogonal function, which may include these continuous spectrum eigenvalues. So u operator, so you can have u of q with constant u. This may be a constant u. Maybe some part of this. It's u times phi of q. So solution of phi, of course, contain the constant u. Solution may also contain the main differential equation. So it's part of that constant which is included in the solution. So if we see it, so these you want to formulate this statement as a statement, we can say that the eigenfunctions defined by first Schrödinger equation constitute orthogonal set and that the eigenvalues are real numbers. So eigenfunctions defined by first or constitute orthogonal sets, and so they are the values are real numbers. So how we can say they come out to be real numbers? We see it. So it comes as a property. Maybe that's why we, in the first place, Hermitian operators, the solution of so they have a spread. That's why we choose Hermitian operators, because their solutions are real, and in the construction of that inner product. So we'll see how they can be real also. But the question is, they are orthogonal. They belong to an orthogonal set. So there can be some other operators which I was non-commuting operators or commuting operators. So in quantum mechanics, the special type of operators we have, which are linear and Hermitian. So if they are linear and Hermitian, an operator U operator, which can act on functions phi plus chi, and so they satisfy this individual property. U operating on this, U individually operating on phi, and U individually operating on chi. Or if there is a U operator operating on k dot phi, it's k dot U of operator phi. So it's the k as a scale, it will come outside. So operator and the scalar can be taken outside the multiplication. Or we can say the inner product of from this the other property 1, property 2. So other property is that U operator acting on phi, the inner product. This operator acting on phi, you can say as it. So you just this operator as a quantity, you can say phi. So you can operator is acting on this U operator acting on chi. So U operator acting on phi, you can you can change the place value of operator from phi to chi. So it's one and the same thing. So we can prove for an orthogonal set just for a later condition. So if phi is chi, then U operator acting on phi is equivalent to phi U operating on phi. So if it comes out to be minus, then you can see it. If you do it here, it will be minus is equivalent to 0. Or U of phi minus phi of U phi is 0. Or if you just get it outside, it will be Hermitian conjugate. So U and outside U of phi minus U dagger phi of phi. So from this U, if you get U minus U star, phi of phi is 0. So I forgot to say, now we can justify this statement this thing. So you can say this thing, U minus U star is 0. So it means division by this is permissible since phi star is 0. So the inner product of phi and phi is 0 only if the function phi vanishes. Otherwise, it's not 0. So if it's not 0, this means U is equal to U star. So this is our how we can have orthogonality of the orthogonality condition that phi is equal to 1 means for orthogonal functions phi. So this means this is an orthogonality condition. Yes. So such functions do not have this thing. Now this present phi is 0 is not derivable from the corresponding. So there is a class of function that's known as a continuous eigenspectrum, which constitutes the Schrödinger equation. That continuous eigenspectrum of Schrödinger equation solution, it corresponds to an orthogonal set. So if you read von Neumann's mathematical foundations of quantum mechanics, there is a more elaborate way of saying the same thing, or more rigorous way of saying the same thing. So now we come to the other property. Other property is other is the commutation rule. So now we are coming to that. I had jumped the gun before, but maybe so you can postpone my prepone my gun jumping thing to now. We are reached to how two operators, for example, may or may not two operators may or may not commute. So V operator, U operator acting on phi. So you can just change. You can have a U operator, V operator acting on phi. So in this first case, you can have this operating on this. This can be function, and then that's being operated upon this. And in the reverse case, V is operating on this, then it's being operated on. So the question is. Here, the combination of two operators, which can itself be taken as a new operator or product operator. So where you can say U operator, V operator acting on phi minus U operator minus V operator, U or V operator, U operator acting on phi. We can also write it like this. U minus, so if I just VOP minus VOP phi. Exactly. So the question is, if for example, UOP, VOP minus VOP, UOP is 0 acting on phi. So this means that U has it's operating first on this. This is an operator, then it's so it doesn't matter. The sequence doesn't matter. Whether this will operate on function first or this will operate on function first. So in that case, this is called as commutative. And if UOP, VOP minus VOP, UOP is not equal to 0, so it's commutative. This is non-commutative. So there can be non-commutative entities and there can be commutative entities. That's it. It can be shown that commutative operators or entities have same system of eigenfunctions, although they might have different eigenvalues. So for example, U square might have same eigenvalue, but they might have different eigenfunctions, they might have different eigenvalues. So the proof of it can be shown like this. For example, if I change the ordering, so V of op, if I check ordering, so V operator and U operator will be acting on phi, will be equivalent to V operator, for example, V operator, U operator. So you can write it U operator acting on phi as U of phi. In the same, now you have a U operator here, so U operator, V operator acting on phi. So you can write U operator, so V operator acting as V phi. Yes. or V operator acting on phi. So disregarding the case of degeneracy, disregarding the case of degeneracy, where different eigenstates or eigenfunctions they can correspond to a unique eigenvalue. Disregarding that thing, otherwise different for commuting operators, the eigenfunctions will have same or identical eigenvalues. So that's it. And we can extend the case to, as a remark, we can extend the case for degeneracy also. But for example, if we have elementary operators, P operator and Q operator, which are defined in, which we have defined as like, if we remember, we defined the Pi as H, Pi as H of 2 pi iota d by dq I, and P square as H square by 2 pi I square d2 by dq square, and FQI as multiplied by F of QI. So if we had a previous definition of how we define the thing, so you can see for how we can define POP, QOP phi for these QOP, POP phi. So Pi is this d by d h over 2 pi di by dt. So you can see it. So we get h this outside the bracket. So it's d by dqi. This is q dot phi minus q is same, and pi can be d by dqi of phi of I. Phi I. So here you will have two terms. One terms it will be dq, it will be phi I, phi I. The second term will be qi d phi I by dqi minus q d phi I by dqi. So it will cancel with this. It will be multiplied by h over 2 pi iota. So at the end we got h phi by 2 pi iota. So for the simplest case, P operated Q operator on phi minus Q operated P operator. For simplest case, we can say that it did not come out to be 0, it came out to be something. If we impose these value of operators P's and P square initially, for this simple case, these operators don't commute. They can be non-commuting operators, and the commutation rule is known. This is commutation rules. And for non-commuting operators, we can have canonically conjugate parameters, just like in classical mechanics. So in the same way, we have Pi and Qi are canonically conjugate parameters. For them, they cannot, the operators do not commute, or rather they are not commutative, not commutative. But you can take, if you take same set of values, Pi's and Qi's, so they will naturally, for the same set of parameters, position, moment, energy, time, so they will not, they will commute, they will be commutative. For other things, they will not, for example, energy, time, position, momentum. So these set of entities, the operators can be non-commutative. So the words, if we want to write these things in words, we can say any entity which is function of P alone is commutative with P, but not with Q. and vice versa. A function of Q is not commutative with P, is not commutative with Q, and is not P, sorry, is not commutative with P. Functions both P and Q, however, can be non-commutative with both Q and P. For example, you can have in your earlier classes we have a angular momentum as a quantity. Where position and momentum px is not x, px is not equal to xpx minus pxx is not equal to 0. Yes, that's it. That's the classical thing. Angular momentum as a non-commutative, the operators as a non-commutative property. So I'll stop here.